Alright, hell yeah. MIT Open Courseware Engineering Dynamics. And we're still on this first problem. This is probably the last part of it because we're doing something cool. We're basically saying that this football gets kicked and this path, we want the equation for this path. And so if we draw our axis, this is the x direction and it's going to be in feet. This is the y direction, it's the height, and it's also going to be in feet. So this equation right here will be y is like, something x squared. So that's going to be, what this equation is going to be. Now, when we use kinematics, we know that gravity is negative 32.2. This is going to be the acceleration in the y direction. So right here we have negative 32.2. Now in the x direction, we don't have any acceleration. This value comes, I should be using that, force of gravity is gravitational constant, mass of the football, mass of the earth, radius of the earth squared. And then writing F equals ma. And then solving for a is going to be F divided by m. You're going to have this divided by m. That's just going to cancel out one of those m's. These three terms are gravity. Okay, hell yeah, now that we're up to speed. Okay, and the reason we don't have any acceleration in the x direction is there's no earth over here. Cool. And with vectors, we can figure out what's going on in this y direction, what's going on in this x direction. So this acceleration, definitionally, is change in velocity, change in time, or dv dt. So it is a function of time. We're saying, hey, every second, I'm going to change my speed by negative 32.2. So we have some upward velocity. Every second, we're going to lose that until we come to a stop, and then kind of gain it in the negative direction, come back to Earth with some speed. All right, so that process is taking that acceleration, integrating it, getting the time value. You have to add a constant. Basically, when this is 0, we know our velocity is going to be 80 sine 60. So this is the constant right here. We're going to integrate again. This goes to t squared divided by 2. That's why this is half. And this picks up a t at time is equal to 0. Both these get blocked out. We have a position that's just 0. So we don't have any constant of integration. That's going to be 0. In the x direction, kind of same thing, just a little bit easier. Acceleration is 0. We don't have any function of time. We just pick up a constant, and that's going to be the component of the velocity in that direction, 40 feet per second. Integration for position is just picking up a t. At t is equal to 0, I'm going to set the position 0. So we have our coordinate system right there. All right, hell yeah. So we're getting close. We have y as a function of t. That's the coordinate in the y direction, and then we have the coordinate in the x direction as a function of t. You throw in the same value here. Let's throw in 1 second. We're going to be going 40 feet this way, and we might be up at, let's see if this thing's drawn to scale. I don't think it really is. Yeah, if we were right here, we're going to be at a height, right there. Sweet, so that'd be like 1 second. It's definitely going to take 2 seconds to get to the top of this arc and then 2 seconds to get back. It's going to take more than 2 seconds, so we might be like right there in 1 second, and then there in 2 seconds, there in 3, and then coming back down with some speed. So, hell yeah, so it's probably not too drawn to scale. Okay, so how do we get this equation? How do we get like this height y as a function of any distance x right here? Well, we have y is equal to this equation with a bunch of t's in it, and then we have x is equal to this equation with a bunch of t's. So what we're going to do is just solve this equation for t, and we get, we get this. And so we can just plug this t right into there, and we can plug this t right into there. Then we'll get y as a function of x. So that's what we do here. Just drop the 40 downstairs, and we get t is equal to x divided by 40. Just a couple different ways to write it. When we plug this t in, we're going to get x divided by 40 squared right there, and then x divided by 40 right there. So we have a function of y as, and I even graphed it. We got 3 different graphs going on here, but this red one, basically this football is on the ground, we kick it up, gets to some sort of height, it comes back down to Earth, And so there is our function, and that's what we have right there. But now the question says is, when is it going to hit these grandstands? We have these grandstands, they're at a 45-degree angle. They're 55 feet away from where we're going to kick the football. And so this method is using the equation method. We know that if we just solve for this equation, y is a function of x, and then we know, hell yeah, this is an equation. It's probably going to run into the y-intercept down here. So the first thing is, like, how do you find this equation? We start with the equation of a line. That's going to be y is equal to mx plus b. And we already know the slope. It's the slope of 1. Rise over run, it's in the positive direction, h divided by h. So I'm just going to write that in so we know that y is equal to h. We're getting closer. We still don't know where it's going to cross this y-intercept. And so, I don't know if there's other strategies, but this is the one that I picked up today, is just like, well, if I know any point on this line, it kind of feels like you're doing the integration process of being like, okay, I know something about this, and this is the integration process, where I know this line has to have a slope of 1. I just don't know, it might cross the origin, I don't know where the grandstands are. So the grandstands we're not kicking the football from the base of the grandstands. And so, but all we need to know is just one point. And I know this point on the grandstand. It's 55 feet to the base of the grandstands. That's going to be a y direction of 0, because we're right there, and then an x direction of 55 feet. So I have x, y, 55, 0. I'm going to plug that in. So here's 0, here's 55 plus b. This equation has to be balanced, and so we have b is equal to negative 55. All right, now we got the equation of our line. So we have y is equal to x minus 55. We also have this equation, y is equal to, something x squared plus something x. Hell yeah. And so, cool, we have these two equations. And now what? Well, we want to find the point where these two equations intersect. And so this is the equation method, where we don't have to know anything about time. We already kind of did that part where, where we said that these two coordinates, this x and this y, anything along the path is these two times are going to be the same. I don't know, I might have misspoke, I don't know exactly how the magic works, but hell yeah, when you solve for this as a function of time, you can input it into there. And yeah, we just have a function of y, that's the path, so that's kind of cool, and it's just a function of this position. And cool, since we have these two equations, we're just going to set them equal to each other. And let's do one thing. Well, yeah. So why can you set these equal to each other? Maybe we have an equation right there and an equation right there. If we see where they intersect, let's say this is equation 1, this is equation 2. Well, this is x1 and x2, this is y1 and y2, and we can see that, hey, these two have to be equal. x1 has to equal x2, and then y1 has to equal y2. And where x1 equals x2, at the same time, y1 has to equal y2. Cool. So, oh yeah, so that really helped me out, because, hey, I have both these y's. I can say both of these y's are equal to each other. Cool. So then I can just put this right there. That's what I do. X minus 55. But I'm glad I did this, because both, like, both are obvious when you graph it like this, but then, now I have all these x values. Maybe this was x1 right there, but then these are x2, So I'm glad I caught that, where it's just, I was just thinking, hey, they're all x's, but that's the reason why. It's like, all these x's are now the same, so we can just kind of get rid of those subscripts. And now we can just solve for this x location. And that's going to be the location where they intersect. Cool. And so all I use is, I just use my graphing calculator to solve it. But I do, if you want to use a quadratic equation, here's my a term. Since this is my x squared term, my a term is going to be negative 16.1 divided by 40 squared. My b term has the x in it. But this also has an x in it. So we're going to have 80 divided by 40, sine 60. And then we're going to bring this x over here. We're going to subtract 1. So cool, that's my b term. C term is just this constant over here. It's going to be positive 55. All right, hell yeah. So now we have this equation graphed. And so to graph this equation, I just took this over here. And I get this blue line. And, you know what I mean, this blue line, it doesn't physically represent, I actually don't know what it physically represents, but I do know when it crosses the 0, you know what I mean, when this equation is satisfied, the x that makes this equation balanced, or if I get this to the other side, the x that makes this side 0, after I do that, is going to be my value of x. So I'm going to do a 0, a left bound, a right bound, and a 0, and we get 118.7. So hell yeah, so we get 118.7 feet. Now that's the value from here all the way to this x coordinate, and I want to know my y coordinate. A lot of different ways to do that, and there's 2 different ways to do that. I got 2 equations that when I throw in this x, and I'm glad I did this, if I throw in this x, I can either throw, both of these x's are the same, so I can use that x in this y1 equation or this y2. And so easiest to do would be put this x right into here, and we'll have 118.7. So we have this y is equal to x minus 55, and that's this equation. Where they intersect is this height. That's what we're interested in. So I'm just going to say y is equal to h, x minus 55. 118.7 minus 55. Sorry I wrote it so small, but we get 63.77 feet. Now I could have also thrown this x into which equation? This equation right here, and that would have also popped me out. Well, let's do that. So let's see what equation this is, and then we'll call it. This is the red equation. So I'm going to go value of x, and heck yeah. So I'm obviously right at where the grandstands intersect, and I'm where this equation for the football intersects. And I just think this gets underlooked because your kinematic equations are functions of time, and it's just kind of cool that you can put them together and get a function of the actual position as seen from a side view. And so that's what we did today, and we used that, and we saw that the grandstands is also a line, because that's the way that kind of makes this problem make the most sense. Is like I can physically see the grandstands, even though they're just right here. I can, you know, project them that way, and I can see the path of that football. So that's what we did. Maybe I call it the equation method. I don't know what you call it, but yeah, hell yeah. We got an equation that's not a function of time. It's a function of x. This was also a function of x. And we know that the intersection from this is both x's are going to be the same. At the same time, both y's are going to be the same. And I'm glad I picked up on that on the fly. So hell yeah, thanks for joining me on this one. And that's a video.